Hi, you're welcome to the 9 lecture. And in this lecture, we'll be looking at smart energy, what if analysis. So this is just the advanced streamlits for what if scenarios. So permit me as I take you through today's slide. So in today's model roadmap, we want to look at the potential energy savings, which is accounted to be 1.9 billion. And when it comes to projected efficiency gain, we have about 53 million. And expected cost reduction has 10 million. So our learning outcome today will be exploring essential streamlit widgets and the core principle of what-if analysis in order to improve the smart energy solution and decision-making processes. So with that, we are going to build sliders, text inputs, and button in Streamlit, which you will be able to learn. And also, you'll be able to work with persist data with st.section_state. And you'll be able to define what if analysis, the counterfactual and the sensitivity score, and also how to derive a voltage saving equation and code it in Python. And lastly, you'll be able to deliver an interactive A/B scenario dashboard with KPI cards. So let's have a refresher. In our day 7 lecture, I took you through the pip install Streamlit and how to run that with the code Streamlit run and then the name of your Python file. So in this case, we have py app.py. And also, I made mention of certain key widgets, such as the st.slider, the st.text_input, and the st.button. And I also said that if you want to rerun your model, the entire script execute on any widgets change. Sometimes you could just go and click on refresh or R and you'll be able to rerun your model. So we also talked about keeping values using the Streamlit section states key equals to value. So let's look at key terms in today's class. So understanding key terms in what if analysis is very important for effective communication and implementation of ML strategies in smart energy solutions. What if analysis. So this helps us to explore different scenarios by altering variables to predict outcome, essential for informed decision-making process. And when we talk about counterfactual, this refers to evaluating situations that do not occur, which helps in understanding potential impact and solutions. It means looking at the future and predicting what could be the outcome and providing solutions for that. And then we have the sensitivity score, which tries to illustrate how changes in input variables affect the output, which is very important for assessing the robustness of the ML model. Next, we have the RMS voltage, which is an effective value of an AC voltage, producing the same power as an equivalent DC voltage. Looking at the KPI card, this is used for displaying headline numbers with optional data. Okay, so we have the apparent power, which is just the product of the RMS voltage and current in regardless of power factor. And then we have the safe operating voltage. In China, it's between the range of 210 to 250 volts, which is being regulated for residential grids, and this helps to guarantee appliance safety. So let's look at voltage, power versus voltage. So if looking at the formula of the resistive load, we'll have this. So the resistance R will remain constant, but the P, power, varies with the square of the voltage. So hence, a small voltage reduction when there's a drop will yield quadratic power savings. So also relative power equation, like our voltage 0 be original voltage and voltage 1 being the reduced voltage, and P is 0 being the original power. So if we are to calculate the savings, it will be the change in P. It means P0 minus P1. So we are assuming that load remains resistive and constant impedance. So motor or LED drivers may deviate. So always validate with field trials. So for saving formula in code, this is what we do. So we define the estimate savings, checking what is the volts old and volts new. That means we're talking about V0 and V1. And in that format, we are setting it to float value, sorry. Then with this, we are trying to put a new voltage which must not exceed the original voltage. And then we check the ratio, which is dividing the volts new divided by the volt old, and that with part 2. Then we have this where the P base is being multiplied by the ratio, and then we are returning round, which tells us the P base minus the P new. Now in all, our expected outcome will be dropping from 230 volts to 220 volts at 3 kilowatts load saving approximately 0.27 kilowatts. Now what example given? So imagine we have P0 at 3, V0 at 230 and V1 at 220. Mathematically, if we impute those values, we are going to have 2.73 kilowatts. Okay, so this will be the result of what we are going to save. Okay, so for Streamlit implementation, let's consider a single scenario. So we are going to import Streamlit as st, put the title, tell what is the voltage 0, load that, and the V1, which is the Streamlit slider. So in this case, we have the number inputs where we are putting the original voltage. In this case, we have range 210 to 250, and we are considering value 230. And in this case, we have current power 0 to 10, considering 3.0. Okay, so in the V1, we have 210, V0 value 220. And then we are to find the savings, which is to give an estimate savings V0, V1, and considering another parameter load. So we are going to create columns, 2 columns, column 1 and column 2. Column 1 is going to record the power save, whereas column 2 is going to record the reduction. And this is what we are going to have. Now, looking at the scenario comparison also, this is the line of code we are going to use. So we are going to code these things and also see the subsequent results during our coding section. Also, if we want to save our call, we will go ahead to use the matplotlib.pyplot as PLT, and we're able to plot that. First of all, we need to tell what is the voltage, the X value. So for the voltage, we are using np.arange. Then we put the parameters needed. And at the plot, we are trying to say plt.subplot. And our fixed size, we are saying 6 by 3 inches. Assigning that here. And here we are saying ax.plot function, ax.setXlabel function. This is to help us label our X axis, whereas this is to label our Y axis. And then we fix the title and then set the plot running. So interpretation calls steepens as voltage falls. So it reduces, diminishing returns near lower limits. So that is all we have for this lecture, which is presentation 9, day 9. So if you want to look at the code where we will be implementing the what if analysis, do well to watch my next video on what if analysis. If you're just joining us for the first time, do well to like, share, and subscribe to this YouTube channel. Thank you for watching. I'll be signing off now. Bye.